mystery interstellar object that was spotted by astronomers last week. It could be the oldest comet ever seen. It's only the third time that we've actually detected an object that has come from beyond our solar system.
The sky just gave scientists a new mystery. Fresh data from the James Webb Space Telescope changed what many thought about the interstellar visitor named 3I Atlas. They show a different mix of gases than common comets.
That glow was cigar-shaped. It was 10 times longer than wide. It's just not clear what this object is. There is a cloud of gas around it that is mostly carbon dioxide.
The result raises serious questions. But here's the twist. Before astronomers even finished tracing its path, the James Webb data suggested something no one wanted to admit. If this isn't a normal comet, then what is it? How we found it? On July 1st, 2025, the Atlas Survey Telescope found a moving object in the sky. The survey is run by the Asteroid Terrestrial Impact Last Alert System team and uses wide-field cameras from Haleakala in Hawaii and additional units in Chile. The Discovery team reported the object and gave it the temporary tag Atlas. The orbit calculations quickly showed a hyperbolic path, which means the object came from outside the solar system. Astronomers assigned it the interstellar label 3I Atlas when those early orbits did not match a bound path. Observers from Cerro Pachon in Chile, Mauna Kea in Hawaii, and sites in Namibia and South Africa confirmed the track. Early photometry showed a faint coma in some images. The small glow suggested volatile material was present, which raised the possibility that the object is a comet rather than a bare rock. The discovery set off a rapid follow-up by many teams, including the European Southern Observatory, Gemini Observatory, Lowell Observatory, and NASA teams. Telescopes measured speed and incoming direction. The object was fast, moving at tens of kilometers per second relative to the Sun, which matched interstellar velocity expectations. Accurate orbit models used observations from multiple nights to rule out a bound orbit. Within days, the object was labeled interstellar, and many groups prepared instruments to watch it as it moved toward the inner solar system. Scientists also tracked its future path. NASA calculations show that 3I Atlas will reach perihelion near October 30th this year, at about 1.4 astronomical units from the Sun. The closest it will come to Earth is near 1.8 astronomical units, so it poses no impact risk. These numbers helped scientists plan observations for before and after the closest solar pass. On August 6th, the James Webb Space Telescope used NIRS-PEC, its near-infrared spectrograph, to observe the object. The instrument breaks light into a spectrum and reveals molecular emission features that identify gases. The Webb team, led by Martin Cordiner at NASA Goddard, recorded spectra from 0.6 to 5.3 microns. The data were processed, and the team released a preprint that listed detailed measurements. Webb observed the comet at about 3.32 astronomical units from the Sun while the object was inbound. Early Webb images showed a brighter coma on the Sun-facing side, which suggested sunlight was driving activity. That pattern is common for comets when the Sun heats their surface and causes gases to leave the nucleus. The Webb observations gave a clean set of infrared fingerprints that other telescopes could then compare. This early coordinated effort set the stage for a rapidly growing dataset that included space and ground assets. But here's where things took a strange turn. Because Webb didn't just confirm what astronomers expected, it revealed something unusual, something almost unsettling about this comet's chemistry. What exactly did Webb uncover? What Webb saw? The James Webb Space Telescope observed 3I Atlas on August 6, 2025, using the near-infrared spectrograph. Webb recorded light from roughly 0.6 to 5.3 microns. Those wavelengths reveal molecules that glow in the infrared. The dataset came from a team led by Martin Cordiner at the National Aeronautics and Space Administration Goddard Space Flight Center and collaborators at several universities and institutes. Webb observed the object when it was about 3.32 astronomical units from the Sun. The spectrum was clear enough to identify multiple molecular bands and to measure relative strengths. The most notable result is a coma dominated by carbon dioxide. The infrared bands for carbon dioxide are strong and easy to see. The Webb team measured a carbon dioxide to water ratio near 8.0 with an uncertainty close to 1.0. That value is far above the typical ratios reported for most comets at the same distance. Water vapor appears in the spectrum at lower levels. Carbon monoxide is present but weaker than carbon dioxide. The spectrum also shows the sulfur-bearing molecule OCS at detectable levels. Small grains of water ice mixed with darker dust appear in the data as broad features and a characteristic infrared slope. Webb did more than identify the molecules. The instrument provided spatial detail across the coma. The data show stronger emission on the sun-facing side of the nucleus. That pattern matches what happens when sunlight heats the surface and causes ice to vaporize. By measuring brightness at different positions, the team derived production rates for each species. Production rates tell how many molecules escape per second. These numbers allow scientists to quantify how active the surface is at the observed distance. A high carbon dioxide fraction raises several possible explanations. One is that the body formed in a region with abundant carbon dioxide ice. Protoplanetary disks have temperature zones where certain ices freeze out, so formation location matters for composition. Another possibility is surface processing. Long exposure to cosmic rays and interstellar radiation can alter surface layers and remove some volatile molecules. If surface layers are lost or changed, the active layer that releases gas when heated may show a different mix than the deep interior. A third idea is thermal shielding. A dust or crust layer could limit heating to shallow regions, so more volatile carbon dioxide at shallower depths could dominate release while water stays locked deeper. The Webb paper compared 3 I-Atlas to known solar system comets. One comparison mentioned is Comet C/2016 R2 Pan-STARRS, which has an unusual carbon-rich chemistry. Even with such comparisons, 3 I-Atlas sits well outside the normal distribution of carbon dioxide to water ratios. The team provided numerical uncertainties and band strengths so other researchers can test their own models against the published values. Those numbers permit direct comparison to Jupiter family comets, long-period comets, and known outliers. SPH-REX, the spectrophotometer for the history of the universe, epoch of Ryanization, and ICES Explorer, observed the object across a different time window from August 7th to August 15th. SPHERE-X covers complementary infrared bands and provides independent confirmation of the molecular signatures. When two instruments record similar patterns, the case for a real detection strengthens. The combined Webb and SPHERE-X data form a more complete picture of the infrared behavior during early August and reduce the chance that a single instrument artifact explains the result. Using Webb production rates, modelers can estimate the fraction of the surface that must be active to produce the measured output. Those estimates depend on assumptions about surface temperature, sunlight incidence angle, and grain properties. The models produce ranges for active area and volatile inventory. As the object moves closer to the Sun, these numbers can change if new vents open or if fresh material becomes exposed. Observers will update models as new measurements arrive to refine the active area estimates. Infrared spectral slopes and specific features also reveal grain sizes and the dust-to-gas ratio in the coma. Webb data point to small, icy grains mixed with darker refractory dust. That mix affects how the coma scatters light and how the tail will form. The presence of water ice grains at 3.32 astronomical units indicates that some volatile material can survive at this distance, while carbon dioxide dominates the gas output. Grain properties inferred from the spectrum help link gas detections to the visible appearance seen by optical telescopes. The Webb preprint lists named authors from institutions in North America and Europe, including the National Aeronautics and Space Administration Goddard Space Flight Center, and the Catholic University of America. The team released production numbers and uncertainties so that other observatories can compare their measurements. These values will anchor follow-up studies and guide planning for radio, optical, and ultraviolet campaigns as the object approaches perihelion. Planned follow-up includes radio arrays such as the Atacama Large Millimeter/Sub-Millimeter Array, the Northern Extended Millimeter Array, and the Hubble Space Telescope. Ground observatories like the Very Large Telescope and Gemini South will monitor changes. These coordinated campaigns will refine composition and gas velocity measurements and timing. But here's where the story takes a sharp turn. Because while Webb mapped the big picture, the ground teams began uncovering details that didn't fit expectations. What strange truth was hiding inside 3I Atlas? Team on the ground and strange metals. Those working on it filled in the details that Webb could not see. Observatories around the world pointed their instruments at 3I Atlas, and each added a different piece of evidence. The Very Large Telescope in Chile observed the object with high-resolution spectrographs. Those spectra showed narrow emission lines that matched neutral nickel. The nickel lines stood out because the iron lines that normally accompany nickel were weak or absent. This contrast surprised many observers. Spectra, with clear nickel but little iron, suggest special mineral mixtures in the dust. Nickel can sit inside sulfide minerals or in metal grains that release atoms under certain conditions. Iron often sits in silicate minerals that break down differently when heated. Laboratory studies of meteorite analogs show that nickel-bearing phases can release metal atoms at lower energies than iron-rich silicates. Mechanical breaking of grains or selective thermal release could free nickel while iron remains bound. Observers considered how atoms leave dust. One process is thermal desorption, when sunlight warms grains and atoms evaporate. Another process is sputtering by high-energy particles or ultraviolet light that knocks atoms from grain surfaces. A third process is fragmentation. When grains break into smaller pieces, trapped metal atoms can escape. Each process depends on grain composition, porosity, and size. Those scientists used line widths and velocity shifts to infer how the metals moved relative to the gas. Lowell Observatory in Flagstaff reported the detection of the cyanogen radical on August 19th using the Hall 42-inch telescope. The CN signal showed up in narrowband photometry and in follow-up spectra. Other radicals, such as C2 and C3, were weak or marginal. Multiple researchers later reported that CN strength rose as the object moved inward, showing volatile organics became more visible with higher solar input. Radio arrays are important for independent checks. The Atacama Large Millimeter/Sub-Millimeter Array and the Northern Extended Millimeter Array searched for carbon monoxide and other molecules. Radio telescopes detect rotational lines that confirm molecule identity and measure line shapes and velocities accurately. In the past, observers used radio arrays to measure high carbon monoxide in interstellar comet 2I/Borisov. Similar radio results for 3I Atlas would back the infrared numbers and add velocity detail. Gemini South on Cerro Pachon took deep images with the Gemini Multi-Object Spectrograph on August 27th. Those images revealed a growing tail and an extended coma. The tail reached many thousands of kilometers in projection and contained a mix of dust and gas. From analysis of the images, these researchers estimated grain sizes and scattering behavior. Small grains scatter blue and green light differently from larger grains. Combining optical images with infrared spectra lets observers link gas release to visible dust patterns. Astronomers' telegram posts kept the community updated with shortlisting dates, instruments, and line detections. These reports let the team of different researchers plan a follow-up and helped amateurs know what to look for. Telegrams showed a pattern: evolving activity with metals and CN appearing after initial detections dominated by dust. Researchers used the ground data to build physical pictures. Metal detections change assumptions about dust composition and about how heat moves through the surface. If nickel appears early, models must include mineral phases that release metals at lower temperatures or by non-thermal processes. Dust-to-gas ratios estimated from images and spectra helped quantify how much solid material leaves the nucleus compared to gas. Those numbers change with time and with distance from the Sun. These different groups of researchers also measured production rates and compared them to infrared values from Webb and other space instruments. Comparing production rates across instruments helps validate results and reduces the chance that a single instrument artifact drives an odd number. When ground and space values agree, confidence in the composition picture grows. For now, the metal and CN trends remain active topics. Observers plan more high-resolution spectra and radio data to refine ideas about mineral carriers and release mechanisms. The combined ground and space data give a changing portrait of 3 IATLAS that differs from many familiar comets. Amateur astronomers continue to supply useful images and photometry, while professional researchers prepare peer-reviewed papers to explain changes and publish detailed analyses over the coming weeks and months. But here's the twist. While data from world-class instruments built a careful scientific picture, a single photograph threw everything into question. Could one eerie green glow rewrite what we thought we knew? More information and what we still do not know. On September 7th, during a total lunar eclipse, astrophotographers Michael Yeager and Gerald Riemann captured images of 3I Atlas under dark skies. Their photos showed a distinct green tint in the coma. Media outlets highlighted the images and described the comet as glowing green. The green color created curiosity because a green glow in comets has precedence in other cases, where molecules such as dicarbon or CN produced visible emission bands under sunlight. The optical spectroscopy that followed detected CN in the coma. CN can contribute to a greenish color when it fluoresces. Dicarbon remains a candidate for the green color as well, but current spectral sets have not provided a clear detection of the dicarbon bands. The photographic green may combine light from molecular emission and scattering from fine dust grains. Observers saw that the green signal appeared stronger on the sun-facing side in some images, which matches patterns seen in the infrared, where outgassing is enhanced on the sunward face. Photographic technique mattered. The eclipse reduced background light and allowed long exposures that pulled out faint features. Image stacking and accurate tracking kept the comet centered while the stars trailed, which emphasized the coma. That effort allowed skilled astronomers and photographers to show subtle color shifts that might be missed in quick snapshots. Despite striking images, several key unknowns remain. The nucleus size estimate is uncertain because the object is not clearly seen in most telescopes. Brightness-based size estimates rely on assumptions about the surface reflectivity. If the surface is dark, the object must be larger to produce the observed brightness. If the surface is bright, then the nucleus may be smaller. Press reports suggested comparisons to a Manhattan-sized area. Those estimates are rough and depend on the assumed albedo and dust contribution. Another unknown is the internal layering and porosity. If 3I Atlas has a fluffy, porous structure, heat moves differently than in a compact body. Porosity affects how volatiles escape and what atoms are released. The mineral carriers of nickel and other metals remain unidentified in current spectra. High-resolution spectroscopy at different times and laboratory analog studies will narrow the possible materials. But here's the twist. What if those gaps in the data aren't just limitations, but hints of something stranger? Could 3I be telling us a story nature alone can't explain? Natural comet or something else? Avi Loeb from Harvard wrote information that drew attention to anomalies in the data. Loeb described odd features and asked whether natural comet models fully explain the observations. He suggested that the community should remain open to alternative hypotheses and that the object deserves close study. Loeb and colleagues framed their commentary as speculative and focused on encouraging more observations. NASA even released statements that current data are consistent with a natural cometary body. Researchers pointed to plausible formation scenarios that produce high carbon dioxide abundance, such as formation near a carbon dioxide ice line or long-term processing in interstellar space. Those scenarios are based on known chemistry and physics. The discussion echoes past events. The first interstellar visitor, 1I/2017, known as Oumuamua, showed odd motion and little or no visible coma. Researchers discussed the cause and proposed several natural explanations for the non-gravitational acceleration while stating that no clear gas signature was seen. The second confirmed interstellar visitor, 2I/Borisov, displayed strong cometary activity with a coma rich in carbon monoxide relative to water. Borisov showed that interstellar comets can have very different chemistry from each other and from typical solar system comets. Comparing the three bodies helps provide context. Oumuamua lacked a clear gas signature and showed non-gravitational motion. Borisov was carbon-rich and acted like a comet that formed in different conditions. Now 3I Atlas has a carbon-2-dominated coma, water and other molecules at lower levels, and evolving metal signals. The differences suggest a variety of formation places and histories among interstellar bodies. Media outlets and science organizations responded quickly to the Webb result. News coverage ranged from science articles that explained the measurements to opinion pieces that speculated on broader meaning. NASA published a science page with basic facts about the orbit and the timeline, and space agencies emphasized that the object does not threaten Earth. Scientists stressed that the measurements are solid and that interpretation requires careful modeling. Any new interstellar visitor will attract attention. Social media and news reports may highlight provocative ideas. Researchers ask that the public follow updates from credible sources and official releases. Scientists value open discussion but rely on repeated measurements and model tests before overturning standard explanations. Comparing 3I/ATLAS alongside the others helps provide context. Oumuamua lacked a clear gas signature, Borisov was carbon-rich, and 3I Atlas is carbon dioxide-rich with evolving metal signals. The differences provide a map of diversity in interstellar objects and show that a single example cannot represent all extrasolar bodies. Observers will continue to provide images while professional researchers measure line strengths and tail shape. If unusual spikes occur in metal lines or in CN, scientists will publish new analyses quickly. The mystery of 3I/ATLAS is far from solved, and every new dataset only deepens the puzzle. Is this just an extreme comet or something stranger crossing our skies? Do you think nature alone explains it, or is there more here than meets the eye? Drop your thoughts in the comment section below and stay tuned for the next revelations.